Okie doke. So we're recording now. So let's. So what's the topic for today? So this is the graduate session. So the topic for the day is the origin of MRI, and this. And so why talk about this? Because we know how MRI works now. What's the point of this? And I think it's actually worth talking about it because a lot of the difficulties in understanding how MRI work come from sort of a conceptual change that occurred after the origin of MRI. And so, and to this day, because of the way that people essentially go back to the origin of MRI to talk about something like frequency encoding, it actually really confuses the issue and makes it very difficult, especially for somebody that doesn't have a background, doesn't already have an engineering background in the Fourier transform, to understand really how it works. And so I think it's worthwhile sort of like taking a lecture out to just go over, like, how did MRI come about, and then how was this sort of Copernican change that occurred sort of relatively early in the history of MRI that sort of made it into the way we think about it now. So why don't we talk about this? I actually, my degree, my PhD is in the philosophy of science, actually not in, I studied a lot of biology and geology and not enough physics, but I actually got a degree in the philosophy of science. And so philosophers of science are interested, they're interested in science, but they're also interested in how scientific ideas develop and particularly how they evolve, how they change. So the origin of MRI is definitely a case of this. And you can sort of trace it down to around like 1971, 72. So there's actually there are two people that got the Nobel Prize. The third one probably should have gotten it too, for inventing MRI. And I always start off with this story. So there was an American guy, Paul Lauterbur, who was a chemist. And then there was a British guy, and then another American who were heavily involved in early MRI. So I always like to tell the story of Paul Lauterbur. So he basically came up with the idea of, he was a chemist, but he came up with the idea of doing imaging, in just basically in one afternoon. It was truly back of the envelope type thing, but it was pretty clear that it was going to be a possible thing to do. And so he went to the patent office, and he told the patent, he was all excited. He told the patent office, "Yeah, I got this great new idea for brain imaging. It's going to be the brain imaging of the future." And this was at Stony Brook University, and the patent office said, "Yeah, it's not going anywhere." So they blew him off. And many years later, they said, "Well, yeah, maybe we made a mistake on that one." So he ended up not making any money off of MRI. The British guy made a good amount of money, and then the third guy made money by suing GE. So we're going to talk about sort of the origin of MRI from the original sort of Paul Lauterbur. He has a good book if you ever. I put it in the reference list on the class webpage. But basically, MRI came out of spectroscopy with chemicals, chemical shift spectroscopy, and so what is so we have to talk about that because it's kind of still relevant. You can do spectroscopy. We'll talk later in the class. I'll go over how you can do spectroscopy with I'll put it out, chemical shift it's a hard word to pronounce. So that was something that existed for many years. So, back when I was taking, I always say this, back when I was taking organic chemistry in 1975, I learned how to read NMR spectrograms. And so what's the chemical shift business? So basically what it is, it's a small displacement in resonant frequency due to variable shielding. And so what is the idea? So the idea is that different, so you can do spectroscopy of different kinds of atoms, but say we're talking about hydrogen spectroscopy, so a spectroscopy of protons, as opposed to, say, helium or some other element. So what you can look at is protons in different parts of a chemical compound that have different local environments, and the idea is that the local environments of the electrons of a lot of the other atoms that are around there will variably shield the proton from the magnetic field that's being applied to them. And so the result is that the protons resonate at a slightly different frequency. So just to take an example, we'll just take an example of acetic acid, a simple one. So the acetic acid is the acid part. Here's the acid part. That's the carboxyl group. That's the acid part, and then here's the part that looks like methane. So it looks like, and so basically, if you look at this, you can see there's one proton here next to the oxygen, and then there's 3 protons here. And so those 3 protons are in a different local situation with the carbon than this proton, this hydrogen there, that's next to the oxygen. So if you were a chemist, you would say the oxygen is particularly electronegative, and so it's sort of like the idea is it kind of squeezes its electrons in, and then they shield the proton less. So this guy has less shielding. And so the result is that guy is going to be shifted more. So less shielding, more shift, more frequency shift. So we're talking about what's the frequency? Well, the frequency is just the resonant frequency, the Larmor frequency, whatever, which depends on the strength of the magnetic field. So whatever your B0 is, it determines that particular frequency. But what we're talking about is a shift away from kind of the center frequency. Now you need something to define the center frequency, and there's various ways to sort of define what zero shift is. We won't talk about the details, but what we're talking about is sort of slight shifts in the resonant frequency caused by the chemical environment. So that's basically what spectroscopy is about, to sort of like measure those shifts in frequency. So so many of the hardware aspects, the actual sort of method of doing an RF pulse to stimulate protons or other nuclei, and then doing the recording using phase-sensitive detection, which we haven't talked about yet, but I'll talk about that next week. Most of that hardware, and then even the Fourier transform, that hardware was developed by spectroscopists, like people, just chemists working on, and then it got adapted to imaging, but it already existed. So to some extent, this lecture is out of order. So I haven't said anything about phase-sensitive detection, and I'm going to kind of assume it for this lecture. But we'll hopefully get to it. I mean, we'll get to it next week and very clearly to sort of say what that means. So if you look at what used to be called, or what still is called, nuclear magnetic resonance, they took nuclear mag resonance. They were going to call it that, but the nuclear part scared people, so that's why MRI, they just call it magnetic resonance imaging without the nuclear part. But, it's still nuclear. Almost all MRI is just looking at protons, and it's the proton nucleus. So let's take an example of the spectrum here, and then just say how we get it. So if you're in an organic chemistry class, you would have to do these various kind of problems, and the problems would consist of looking at a spectrum. So here's a spectrum, and the chemists like to plot the spectrum backwards. That's just the way it is. So here's 0, and then here's parts per million. They use a strange system of plotting the frequency shift. So this one is, so basically, so parts per million shift in frequency. So what you're looking at, so why do you call it spectroscopy? Because it's a spectrum. Scopy is looking at something, and spectrum, so it just means looking at the spectrum. And what is a spectrum? A spectrum is is the amount of frequencies across a whole range of possible frequencies. So basically there's just this frequency, which is shifted down a little bit. And then, so this is more shift going backwards, but that's just the way the chemists do it. More shift. So this guy's shifted down more than this one, and then this is a spectrum, which has frequency on the x-axis and amount on the y-axis. So that's what spectroscopy means. So and I have that parts per million shift in. Okay, so if you basically look at the area under these curves in the spectrum, so you can see it's a sharp spectrum, so there's really only 2 frequencies in it. So if you look at the area under this curve, this has 3 times the area of this guy over here, and that makes sense because you've got 3 protons in. If you have a pure sample of acetic acid, then you have 3 protons here on the carbon and 1 on the oxygen. So basically, what do you do this for? So one of the things you do this for is to try to figure out what a chemical is. So using spectroscopy, you can see a bunch of characteristically shifted resonant frequencies, and from that you can actually sort of say something about the chemical. So you can actually, guess what the chemical sample is. If you have an unknown chemical sample, you can guess what it is by looking at the spectrogram of all the protons. Obviously, if it's a more complicated molecule, you're going to get like protein, you're going to get a very complicated spectrum. And they do that spectroscopy of proteins. And the reason is you can do this when a protein is like sort of just floating around and wiggling in a real like in solution. You don't have to crystallize it. You can actually just do spectroscopy of a proton in its native environment. But this is a very simple one, just a very, very simple spectrogram. So how does this work? So you do an RF pulse. So here's RF pulse typically. Now you typically do that. Now that's not the way people did it originally. So the way people did this originally, and this sort of going into this, we see what the reason for the Fourier transform was in the first place. So this is the modern way of doing it, is to do an RF pulse like that, a very short RF pulse. So, but let's just put down here, like, how we did this, originally. So, originally, the idea was start someplace and then slowly ramp the frequency up. So here's frequency like that, and this is time. So slowly ramp the frequency up, and the idea is that, and then record the whole time. Or you could just do it in little steps, like so. Set the frequency. Set the frequency here, do a little recording. Set the frequency here, do a little recording. Set the frequency here, in order to make this spectrogram. And so the idea is that you slowly ramp the RF frequency stimulation and through all these resonant peaks. And then as you get to a resonant peak, there'll be a signal, and then you go a little bit, if you stimulate with this frequency, you get nothing. So obviously this takes a long time. So if you thought, like, say you have a bell that resonates at a certain frequency, if you take a speaker and slowly play a whole bunch of different frequencies to it, slowly changing the frequency, when you get up to the resonant frequency of the bell, the actual sort of bell pitch, what will happen is the bell will start wiggling. Then if you keep going, it will stop resonating. And then if there are harmonics, sometimes it might start wiggling at a higher frequency. So that's the way they did it originally. But that takes a long time. And so an alternative way of doing it, which everybody switched over to very quickly, was let's just hit the bell with a hammer. So what is this RF pulse? So this is a very short RF pulse. It's short, as in, say, like 50 microseconds. So it turns out, and we'll talk about this when we talk about the Fourier transform, but if you have a little spike in time, that actually corresponds to many different frequencies. So doing just like a very sudden little hit, like a hammer hit of RF pulse, will actually effectively stimulate many different frequencies at the same time. It's kind of like hitting the bell with a hammer. And so what will happen is you'll get the whole signal, you'll get all these different frequencies coming out at the same time. So now the problem is, so what does the signal look like when you do that? Well, you get this very rapid oscillation, and I'm just sort of, this isn't doing it justice. This is, if we're at 3 Tesla, this is, 123 megahertz, so 123 million ups and downs per second, approximately. Maybe shifted a tiny bit, shifted 100 or something like that, away. But a very small shift in frequency, but very rapid. And that will contain multiple frequencies. So it will contain like 123.01 and 123.03. So there'll be a couple different frequencies in there, all mixed in together. So how do you fish those out? How do you fish those frequencies out? So the very first thing that you do, you don't actually record this signal. I mean, you can record this signal, but it's got a bunch of very fast wiggly oscillations. So this is RF pulse This is the signal that you're getting. So what is always done is something called phase-sensitive detection. Which we'll talk about next Wednesday, or next Monday. So phase-sensitive detection it basically boils down to finding the frequencies, the frequency offsets. So not the actual 123 megahertz, just like what is the difference between the center frequency of, say, 123.000 and then 123.01. So just the 0.01 is what we're looking for, just the difference. And we'll explain how that works on Monday. It basically just works by taking a reference signal and multiplying by a reference signal. But the end result, that what you get out something that just contains a couple very low frequencies, the frequency offsets. So this is, fine, delta frequency. So, frequency offsets. So in this case, there'll be more than one. So you'll get sort of a complicated thing that's got more than one frequency in it, and plotted out this way. So you'll see maybe there'll be some higher frequencies in it, and then some lower frequencies in it, and then the whole thing is decaying away. So if you broke that down, what does it actually consist of? Well, it consists of, a lower frequency that's dying away, and then a higher frequency that's dying away. So if you add those, that's the thing you get. So this is time. So this is time. Make sure that's time. Okay, so this is the signal in time that contains multiple frequencies, like two different frequencies. So what do you do if you're an engineer and you see something like this? You take the spectrum by taking a Fourier transform. So we take this thing and we do FT, Fourier transform. Fourier transform. And what is the Fourier transform? Well, the Fourier transform changes from time to frequency. So, it changes from the time domain. It changes your signal into a spectrum. So here's your spectrum before the chemists have flipped it around. So we started off with something that had a bunch of samples over time, and we changed it into something that has a bunch of samples over frequency. So that's what so the Fourier transform is a way of sort of picking apart these two frequencies. Not just two, it could do many. So picking apart all these different temporal frequencies. So we're going from so these are, temporal frequencies. Because we're going to talk about spatial frequencies eventually, but temporal frequencies. So we have time, time, and then temporal frequencies, which are sort of frequencies of time. And what does that mean? It just means like there's this much of this frequency across the whole thing, across your whole sampling time. Now, the part that's usually left out of this for psychologists is that this signal is a complex valued signal. So there's actually another signal in here. There's another signal in here. It's a two-dimensional signal. So I'll just this isn't a very good drawing of it, but this is a drawing. So this I should have drawn a different color, but this guy is the real part of the signal, and this guy is the imaginary part of the signal. Now, if you know anything about processing audio, audio information, you probably know, like, if you've got you want to figure out what frequencies are in a speech signal, you take the speech signal in time and you do a Fourier transform of it and you get a graph and it says how much of each frequency. Turns out that the Fourier transform insists on getting a complex valued input. So if you feed in a speech signal, you're feeding in the real signal, and then for the imaginary signal, you're just putting in zeros. So you always need a complex valued input to the Fourier transform. So the Fourier transform, it takes, complex in and complex out. And the thing you're getting here is just one of the numbers. This is called the amplitude spectrum. And what is the amplitude? It's just the amplitude of that complex number at each frequency. So here's, say that's radius 1. So here's a number, and here's the real part of it, and here's the imaginary part of it. There's the angle, and then this guy is the amplitude. That's the amplitude. So that's for one frequency. So for one frequency we have an amplitude, and so we plot that here, and then we go to another frequency, we get another, different, say here's another frequency, very small amplitudes, that might be this guy, small amplitude. So that's what we're looking at. We're taking two numbers in at each time point, and we're turning it into two numbers out at each frequency point. So that's how you get the spectrum. And chemists were doing this because they're just looking for these two different frequencies, which they normally would have gotten just by slowly ramping up the stimulus, and then just essentially sampling each point in the frequency spectrum one at a time. But you could just do it by hammering it with this. Just hammer it with a short pulse, which effectively contains multiple frequencies, get the signal that you get out, and then do a Fourier transform of it to figure out what frequencies are in it. Okay, so we'll go over that again when we talk about how to do spectroscopy on a brain. So you can do brain spectroscopy. But that's the basic plan of spectroscopy. So how did MRI come about? So Paul Lauterbur was a chemist, and so this is kind of the original sin of MRI, because he came up with this. This happens often in the history of science. Somebody will come up with an idea. It won't be quite right, or they haven't thought about it the right way, but they kind of know something. There's a lot of science is kind of sleepwalking. They try to give you this rewritten history of science that you're making a hypothesis and you're doing all these you're acting like a good scientist. It's not the way it works. You just sort of do stuff, and when you're at the edge of what you know, you often don't have real clear hypotheses. What you do is you just sort of see something. You say, you see an analogy between something like chemical spectroscopy and imaging, and then you just run with it, even though you don't really fully understand it. And then later on, people kind of figure it out. And so that's what happened here. So what was Paul Lauterbur's idea? So the idea was, well, why don't we? So there's one more thing we have to say, is the spectroscopist had gradients. So the spectroscopist already had gradients. And what did they use the gradients for? Well, one of the things that happens when you stick a sample into an NMR spectrometer is that the sample sort of messes up the magnetic field. And so you need something to actually sort of fix the magnetic field. And so one of the things that you can use to fix the magnetic field is a simple gradient. And you can have there's higher order shims that are more complicated than just a linear change. You could have something that changes as a function of z squared. So what a gradient is you go along the x direction, the gradient, the strength of the b z component changes as you go in the x direction. And a y gradient is, change the bz as you go in the y direction. A z gradient is change the bz as you go in the z direction. But you could also have something like that, like a squared. So as you go in the x direction, or say the z direction, it changes the bz as a square of where you are in the z direction. So chemists had these. They had a whole bunch of them. They had x to the fourth, all different kinds of different shims. And so Paul Lauterber's idea was, well, why don't we take and just turn a gradient on a sample? And so his original idea was, it's an analogy, and a lot of things are analogies. Darwin's idea of natural selection was an analogy. It was an analogy between artificially selecting plants and animals and something like that might happen out in the real world. It's just a really big analogy. So this is an analogy between chemical shift causes change in frequency. And so what are we analogizing that with? So analogize that with gradient causes change in frequency. Because if you turn a gradient on, that will change the B0, that will change the... So, and then we stimulate with broadband. So stimulate with all frequencies. So I didn't put the heading up here. So this is spectroscopy. And this is, MRI. So stimulate with broadband, and then that's the same. We just stimulate the brain with broadband. And then we time sample. So time sample the FID. So what's the FID is the free induction decay. So that's the signal equals signal. So we time sample. So we get a bunch of time samples of the signal. Time sample the FID containing multiple frequencies. And that's the same here. So that's the same. We just do a time sample of our signal, and it's got multiple frequencies resonating in it. And then the last one. And so the last one is where there was kind of a Copernican shift, sort of like, sun going around the Earth versus, Earth's actually going around the sun. So we do a Fourier transform to get spectrum. And the idea here is, same, except we do, Fourier transform to get objects. And the very first paper in Science magazine on this, they just stuck like two objects in the magnet and just see, could we just actually turn the gradient on and then see, could we actually sort of see those two different frequencies for those objects. Now, what's wrong with that? Well, so then what happened was, this actually is not the way that modern MRI works. Well, it sort of works this way, but here's what the problem is. It's kind of like it is, like a Copernican shift where you're sort of like inverting, like the sun and the Earth. So if we if we look at, let's just draw here. So here's spectroscopy, and here's MRI. And so let's look at what the signal is in spectroscopy and what the result is. So you just have a 2 by 2 here. Okay, so what happened? So the very first image published in Science magazine was like this, but maybe about just a couple years after that, people figured out this Copernican shift, and there was a paper. If you want to sort of go back and read it, there was a paper on the idea of K-space, and you probably have heard of K-space, sort of spatial frequency space. K-space paper. If you go back and read it, it's nearly unreadable in modern terms. But this paper by Donald Twigg was a very important paper on reconceptualizing how we think about MRI, and so what was this reconceptualization? Well, let's first put down what the spectroscopy was using. So here we have samples of oscillations in time. So you've got something like this, you've got something like this, and you have a bunch of samples, which are it's just like an audio signal. You just have this low frequency audio signal coming out, and you just sampled it a bunch of times, and now you're just trying to figure out what frequencies does it contain. And how do you do that? You do a Fourier transform, and a Fourier transform transforms between the time domain and the frequency, the temporal frequency domain. So now we get in to the frequency domain. So now we're in the frequency domain, and so we have a spectrum, spectrum of frequencies. So how does MRI compare to this when we think of it from the Copernican K-space perspective? So it turns out that MRI is exactly the opposite. So what is our data? So our data is not, we're sampling the data over time, just like we are in the case of spectroscopy, but what's going on here is we're now thinking of it as samples of spatial frequencies. So what is a spatial frequency? So notice we're now in the frequency domain. So what's a spatial frequency? A spatial frequency is something like, say you have a face. Here's a happy face. That's an image. So what's a spatial frequency? A spatial frequency is changes in brightness, changes in signal that are uniformly going up and down. So like in the case of the face there, if the background, if the background of the face is all black, like that, and you have the face in the middle, what spatial frequency? This contains many different spatial frequencies, but one spatial frequency it contains is spatial frequency 1, so like a sine wave like that goes like that. So what is just a pure spatial frequency 1 look like? Well, it would just look like, something like an inverted cosine. So it would basically be, bright here, and then it would get dimmer, the other way around. I'm changed my convention here. Let's do it correctly. So here's the face. So there's the face in the middle, and the face is bright, and the background is black. Okay, so this is the spatial domain. We'll talk about this a lot more because this is important to get this idea. So this is the spatial domain, this like time. And this is the spatial frequency domain, like temporal frequency. So here's an example of a temporal frequency. So it's bright in the middle, and then it just goes off dimmer and dimmer like that, and then it starts to get a little more brighter. So the dimmest part is right there, right, off to the side like that. Okay, so if you plotted this, you would have something. If you plotted the brightness, so that's spatial frequency equals 1. So that's a spatial frequency. But notice, it's on the signal side. It's not on the result side. And so what do you have to do to get it? You have to do the inverse Fourier transform. Now, the magic of the Fourier transform is that the inverse is very similar to the forward. It's just kind of, it's just the way it works. If you just do a Fourier transform again, you get back to where you were. You have to put a negative sign in the exponent, but other than that, it's exactly the same operation. Very strange, but we'll try to sort of get an intuitive feeling for why that is. But the result is that you now go back and you generate a spatial object. So now we have a spatial object. And that spatial object, that's like the time domain. It's like the time domain. So you can see the frequency domain is on the opposite side of the signal versus result. So this is the way that people think about MRI now. What you're doing is you're not collecting a bunch of samples of time oscillations and then doing a Fourier transform in order to figure out what frequencies it contains. Instead, what you're doing is you're collecting a bunch of samples of different spatial frequencies, and then you're inverse Fourier transforming it to get something, the spatial object, which is pretty much like the time domain. It's more like your original data in the spectroscopy case. So it really is sort of a Copernican flip in the way you're thinking about this. And it's absolutely critical to understand this in order to really understand how MRI works. So I'll just give one example in the last minute here, which we'll go through in much more detail when we talk about this, talk about the frequency encoding, so-called frequency encoding in the readout. But here's an example. So say we do an RF. So here's how we draw our little RF pulse as a sync pulse. We'll explain what that is. So here's our RF. And typically what we do is we then turn a gradient on. So here's the gradient. And this is during so-called frequency encoding. So-called because there is no frequency encoding. We're going to stamp out frequency encoding. But so-called frequency encoding. And then you record a bunch of samples. So here's data. And you record them over time. So here's a bunch of samples that are recorded over time. So at first it looks like spectroscopy. It looks like you're recording it over time. So these are samples. And you might think, okay, well, just think like this original analogy. You've turned on a gradient, you're causing things to resonate at different frequencies. So you've got this mix of frequencies coming out, and then we're recording a time signal. And then we're going to use a Fourier transform to fish apart all those frequencies. Don't think that way. Wrong way of thinking. And here's how to convince yourself that that's a completely wrong way of conceptualizing this. And so let's do another experiment right alongside this one. So in this one, we turn the RF on. Here's our samples. We turn the RF on, and now we turn the gradient on just for a little bit, like that. And then while the gradient is off, we record a data point. So what does that mean? So we turn the gradient on, it changed the frequencies, and then we turned it off. Now the frequencies are all back to the same. We record a data point, and then we turn the gradient on again, turn it off, and record another data point, etc. And just do this whole thing. You get the same result. It's not exactly the same because there's been some decay, but if we just forget about the decay, or did it really fast, you'd get exactly the same result in this case as in this case. But in this case, it's all the same frequency. You're recording the exact same frequencies because you have the gradient off, and so the frequencies have all gone down to the same frequencies, and yet you get the same thing as this. So that shows you it's not like this. It's not like you're recording a bunch of samples in time, and then which contain multiple frequencies, and then you're using a Fourier transform to fish out all those different frequencies. Because if that was the case, this wouldn't work. How would this work? We've only got one frequency every single time, but the data looks exactly the same as this that was recorded with all those different frequencies. So each point here is recorded with multiple different frequencies on because the gradient is turned on, so at the high end of the gradient there's going to be higher frequencies. And so for every single one of these points, they will have been recorded with multiple frequencies, kind of like a spectrogram. But it turns out that's not required. You can just do it this way and record it with all the frequencies exactly the same and get exactly the same result. So that shows you you're not in, you've changed towns. It's a different way of thinking about it. This is the proper way of thinking about it, that you're doing sort of you're doing samples of spatial frequency that happen to be recorded in time, but that's not important. And then you're doing an inverse Fourier transform to turn them into an object, as opposed to spectroscopy, where you really are recording samples of oscillations that contain multiple frequencies across time, and then doing a Fourier transform to get the spectrum. So often when people are starting MRI, they'll give you this analogy, and once you've got this analogy in your head, you're stuck. You can't get out of it. The engineers can get out of it because they know about Fourier transforms and inverse Fourier transforms, and they'll quickly sort of move on from it. But psychologists will just get stuck at this point. And so that's kind of the original sin of MRIs. That's how it was figured out, but that's actually not how it is currently conceived of. Now you might wonder, how can you do you can do spectroscopy with MRI. You can make an image and do a spectrogram, and we'll talk about how that can occur. But hopefully this will sort of get us off on the right footstep. Why there is no frequency encoding. It's all phase encoding. So it all has to do with these spatial frequencies, recording samples of spatial frequencies. Okay, David, I think I went over just a little bit. Maybe we'll end now, and I'll take some questions.
Yeah, we're still a couple of minutes.
Okay.